Hello all, welcome back to my YouTube channel all about VLSI. In this video, we are going to start with the new topic that is register abstraction level modeling, that is a RAL model. Okay. So in UVM, we have something known as a RAL model. Let us try to understand what is this RAL model. So before going to start discussion of this RAL model, we need to have some basic understanding of few things that we will try to understand. Let's say if I am going to have a simple IP, okay. Let's say if I'm going to have a simple IP, and if I want to bring it to more basic way, let's say this IP is a simple adder, okay, and as well as a subtractor. Okay, so I'm trying to keep the things as simple as possible, so that we will come to know what is exactly happening. Okay, so let's say if this IP is a adder come subtractor, right? Now, if you want to configure this IP to work as an adder, okay, you can. Now, what I'm going to do is this IP will have something known as registers inside it. This IP will inside it is going to have something known as registers. Now, using this registers, I am going to configure whether this IP should work as an adder or whether this IP should work as a subtractor. For example, this register value, if it is updated to 0, then it is going to act as an adder, and if it is configured to 1, then it is going to act as a subtractor. Just it is a simple example of just I'm trying to make the things simpler. Okay, so we are going to have an IP. This IP is going to act as an adder or subtractor, where if we configure this register, we are if we are going to update the value of this register to 0, it is going to act as an adder, and if we are going to configure this register as 1, then it is going to work as a subtractor. And how this register is being used and how it is designed, that are all secondary. But if we are going to look it in from the perspective of a system level, then we don't know what is exactly which is present, right? So we just know that there is a register, and if we configure that register to 0, it is going to act as an adder, and if we configure that register to 1, it is going to act as a subtractor. Now let's say for this adder can have the width of the data to be added. For example, it can act as a 4-bit adder, or it can also act as a 8-bit adder, or it can act as a 64-bit adder, so on. Okay, so let's say the maximum limit is 64 bits, right? So for configuring this type, we are going to have one more register which is of 6 bits. So using 6 bits, we can have the width, right? Okay, so depending upon this particular register value which you have updated, let's say if you have updated it as 0000000, this adder, let's say it is going to add only 1 bit of data. Let's say if you have configured this particular register as some one all ones, then it is going to add 64 bits of data like this. Okay, so depending upon the specification of this IP, you are updating your registers. If you are updating this particular first register, it is going to act as an adder, or it is going to act as a subtractor. And if you are updating the second register value, then it is going to decide how many bits you can add using this particular IP. Let's say this first register name is mode register, and the second register name is width register. So depending upon the mode register and width register values which you are updating, you are configuring this IP, right? So how to configure this IP? You are configuring this IP by updating the values of these registers. Okay, so in any session, we will see how to design a Verilog code, configurable Verilog code, where we can develop this type of registers inside an IP. We will try to have one session. But in this particular session, that is not our main objective. We are going to see the things in the system level perspective, right? So we just simply got an IP from a vendor, and we see the specifications that if we modify this register contents, this is how your IP is going to work. That's it. Okay. Now, taking this particular example, let's scale up the things. Let's say if I'm going to have a simple UART IP. This is a 165050 UART core IP, where I'm going to have a CSR interface and a TX shifter, TXP4, TX flow control, RX flow control, RX shifter, clock generator, RXP4. These are all the things which I'm going to have, and these are the interfaces: clock and reset, and Avalon MM interface, and RS232 serial interface, And these are all the things which I'm going to have inside my IP core. Now, first of all, what do I mean by this CSR? So basically the CSR interface is the register access interface of an IP block. Now, as we have discussed in a simple adder where we are going to have two registers, in our actual IP also we are going to have multiple registers, right? Now, we will have the registers like RBR, THR, IER, IIR, DLL, DLM. So basically this RBR stands for receiver buffer register and its access is read only. So these registers which we are going to have in this particular IP are classified into different types like read only, write only, and read write. Okay, so we will have the access also. So in the case of read only registers you cannot write anything, and in the case of write only registers you cannot read. And we will have read write where you can perform both read operation and write operation. Okay, so in our particular in our IP core also we are going to have this particular registers. RBR stands for receiver buffer register, and it is only a read only register, and the purpose of this register is going to hold the receiver data which it is going to receive it. Okay, and next is THR, which stands for transmit holding register. Okay, which is going to hold the data to be transmitted. Whatever the data which I want to transmit, that particular data will be held inside this particular register. And this is write only register. You cannot read anything from this register, you can write into this register. And I have something known as interrupt enable register, which basically enables all the UART interrupts. And I have interrupt identification register, which is a read only access, and it indicates basically interrupt source. And I have something known as DLL, which stands for divisor latch LSB. Okay, which is a read write register, and which basically helps us to decide the baud rate divisor. Okay, and also I have DLM, which is divisor latch MSB, and which is a read write access, and it is also going to decide the baud rate divisor. So our concern is not how these registers are working and what is the exact meaning of these registers. We are not concerned about that particular thing for this particular session. We are concerned about what do you mean by registers and where are they present and what are those doing. Okay, that is what we are trying to understand. Okay, we have basically started with a simple adder IP where we have seen simple two sample registers, and we have scaled up our discussion to a simple UART core where it is going to have different type of registers, right? Now we may have different registers, and depending upon the specification of the IP we may have extra registers that we will see whenever we are going to see the specification. Now we have something known as CSR. CSR basically it's an interface and it is going to, so basically CSR interface is the register access interface of an IP block. So it allows software or the testbench to configure, control, and observe the internal hardware using the registers. Now, if you want to access any registers which are present inside this IP core, you cannot access it directly. Using this CSR interface, we are going to access that particular registers. Okay, so the CSR interface is helping us to access the internal registers which are present in that particular IP. Now, why we want to access that particular registers? As I have said, if you want to configure any IP, you need to configure the register values. Okay, internal register values. Depending upon the internal register values you have configured according to the specification, your IP is going to work accordingly. Okay, so in our UART IP, the CSR interface sits between the system bus and the internal UART logic. Okay, now the system bus may be Avalon or APB or AXA and internal logic. What are the roles of the CSR interface? It basically decodes the bus address and it maps the address to the registers, and it handles read and write operations, and it updates the control signals to internal blocks, collects status signals from the internal blocks, and when the software writes to a register, the CSR interface translates the write into control signals. Now, what do I mean by this? Let us try to again come back to our adder IP. Let's say, again we are going to have this adder IP, right? Adder or subtractor IP. We have seen inside this adder or subtractor IP, I'm going to have something known as mode register, which is going to decide the mode, and something known as width register, which is going to decide the width of the data which we are going to supposed to add or subtract, right? Now, inside this adder IP, let's say if we want to integrate this IP, or if we want to communicate, if we want to establish the communication between this IP and a processor. So if we want to establish a communication between this IP and a processor, we need to use some bus protocol like AXA or Wishbone, or you can use AHB. AHB is not used commonly. AX and Wishbone are used. Okay. Now, if we want to establish the communication between this processor and IP, we need to use any one of this interface. And this IP should also have this interface related signals. Interface related signals. Okay, it should support either AXA or Wishbone or something. Okay, so depending upon this IP, which interface it is working with, that particular interface we are using with our processor, and we are going to establish the communication. Now, when you are trying to establish this particular communication, for every IP, there will be some address space that will be allocated. Now, what do you mean by address space? So, basically, this IP will have some address space like 002 FF. Let's assume it is going to have this address space. Okay, for example, I'm taking this. So, this IP is going to have this particular address space. Now, as a designer, you are going to basically specify, if you want to access this register, then the address for this register will be, let's say, 01, and the address for this width register, let's say it is 10. Okay, so this is the offset address we are going to specify. As a designer, we are going to specify the address for this mode register and the address for this width register. This is nothing but my offset address. Now, whenever the processor tries to communicate with this particular registers, it needs to specify the address so that the processor can able to find out where is the register which is present. So if my processor wants to communicate with the exact register it wants to, or if it wants to configure this registers, it should specify this particular address. Then only my processor can able to configure this registers, or else it is impossible. Okay, so there will be something known as address space, and this registers will have some offset address. So here also in our UART IP, our registers are going to have some offset addresses. Okay, so this will be already given in the specification, so it will be fixed always. So here this RBR register is going to have an offset address 00. If your processor wants to communicate with this RBR register, then you need to specify this address. And if you want to communicate with this THR register, you want to specify this address. And IER, you need to specify this address. IAR, you need to specify this. And DLL, you need to specify this address. And for DLM, you need to specify this address. So depending upon the address offset you are going to provide, your processor is going to communicate with this particular registers. Now, this 165050 UART IP is a configurable register controlled protocol based design, and its behavior depends heavily upon register programming. Depending upon the register programming which you are going to do, depending upon the values you are going to update in the register, this particular UART will be configured. Now, what are the values that should be updated inside this register? That we will see from the specification, and according to the specification guidelines, we are going to update each and every register value. And for updating the baud rate also, we need to see inside the specification docs, and we need to update the register values and interrupts, FIFO behavior, error conditions, right? Now, if we are supposed to test, or if we are supposed to develop a UVM test bench for this particular IP, okay, now what we need to do, we need to configure this particular register values, right? We need to configure this register values through this CSI interface. We are supposed to configure this register values, and then only we can able to test whether our UART IP is working correctly or not, right? Now, how to test this? So let's say if we are not using register abstraction level modeling, and if I want to test this particular IP, now how to test this? So we need to develop something known as bus transactions, and we are supposed to provide the addresses, and we are going to provide the data values which we want to update inside my registers, update in the registers. And why I need to provide the addresses for identifying which register I want to identifying the registers. So from my test bench, I'm supposed to provide this offset addresses, and I need to provide the data value which I want to update inside this particular registers. So accordingly, my IP will work. Okay. So we are basically going to test our UART by manually writing and reading the bus addresses. Now, let's say if I want to configure 8-bit data, one stop bit and no parity. So I need to know the LCR offset address. LCR is a register, and this register address I need to know. Okay. And also I need to know the word length and value for 8 bits. Okay. So basically this LCR register will be some bits width that we don't know. Until and unless we see the specification, we don't know what is the width of this particular LCR register. Let's say this LCR register is of 8 bits width. Okay. And let's say these two field values, LSB value and LSB value and the next bit value will decide some configuration. Let's say it is going to decide the bits 0 and 1. Let's say it is going to decide the word length. Okay. So depending upon the values which we are going to update here, the IP is going to be configured. Okay. Now, if I want to drive the data into this LCR register, first of all I need to provide the offset address from my test bench, and next I'm going to provide the data. Let's say if I want to set the baud rate, now I need to find out where is my DLAB register which is present. I need to know the DLAB register offset address, and I need to update the DLL register, and I also want to update the DLM register, and I need to update this DLAB register. Now, what are these registers? What are these functionalities? Until and unless we study the specification thoroughly, we do know. Okay. So just in this particular example, for setting the baud rate, we need to update these registers, right? Now, how to update these registers? We have something task. We have a task which is known as avalon underscore write. And using this task, I'm going to provide the base address plus offset address, base address plus offset address, and base address plus offset, base address plus offset. Okay. And next I'm going to provide the data. Here I'm going to provide the data inside my DLM address, DLM register, DLL register, DLAB, and DLAB. Okay. So if I'm providing the address, then that means I'm selecting this register, and next I'm providing the data. Next I'm providing the address, next I'm providing the data. And this will be done from your test class. Okay. So inside your test class, you are going to have different test cases where you are going to provide the address, so that you are going to select a particular register, and next you are going to provide that particular data. So this is how you are going to write down or select a particular register from your test class. Now, what is happening if we are not using a RAL model? We are basically remembering the addresses, that is nothing but my offset addresses. And next we are also remembering the bit meanings. For example, if I'm going to have a 8-bit, each and every field value have some meaning. Let's say suppose if you are updating this 2 bits as 00, this register or the IP will configure it in such a manner, and 01 it will be configured in another manner. Okay. And we are basically tracking the reset values, and we are tracking what we wrote last. Okay. And we are basically repeating this logic in every test. Now, let's say if I'm going to change the bus, let's say if I'm going to change the UART interface, which is basically working with APB interface. Let's say if I'm changing this UART IP, which is basically working with APB interface, to some other interface, then what happens? All the tests which I have written will not be useful, and we need to rewrite all the particular test cases. And let's say if this UART IP or whatever the IP which we are going to have, let's say if it is going to have some LCR register which has the offset of, let's say 3. Let's say if we are going to change it to another offset address 10, then what happens? All the test cases which we have written will be waste, and we need to write down the another test cases where we need to change the offset address for this. And let's say if we have a register, let's say some DL register or something, and this particular field has only read only access, and we accidentally try to write some value into this particular field, then we will get a failure. Okay, so this type of things will happen if we are not using a particular register abstraction level model. So without RAL, our tests are bus aware and our tests are register map aware, and we are bit manipulation and tests are bit manipulation heavy. And our test bench is doing too much low level work. Let's say if this is our IP where it is going to have different registers, and this is our test bench which we have written, which is being connected with our IP using the interface. Now, whatever the register field values which we have updated with our test bench, we will not have a proper track of what are the values which are being updated inside this particular IP. We will not have a proper track of what are the values which are being updated inside this particular registers. Okay, if we are not using a particular RAL model. But if we use a RAL model, then we will have a track of what are the values which are updated inside this particular register fields. Let's say suppose if I'm going to have two registers, then using my RAL model, inside this model also I'm going to replicate this exact two registers inside my RAL model, and whatever the values which I'm updating inside my design inside this registers, those values will be replicated inside my RAL model also. Okay, so this is how my RAL model is basically keeping track of whatever the internal registers are being configured inside my IP in my test bench also. Basically, this RAL model is a clean abstraction between the UVM test bench and the UART CSR interface. So instead of test dealing with the raw bus transaction addresses and bit masking, they interact with the registers and the fields as an objects. So RAL makes the test bench protocol independent, whether the UART is connected through APBEX or any other interface. The test code will remains the same. Only the adapter changes. We will have something known as adapter that we are going to discuss in our later sessions. Only if we change this particular thing, that's it. Okay, so this is greatly improve the this greatly improves reuse when the same UR type is integrated into different SOCs. And RAL model also maintains a mirror or shadow copy of a register values. This is what we have discussed previously. So the RAL model knows what expected values of each register should be. So this allows automatic checking of reset values and detection of unexpected register changes. And let's say if our RAL and also our RAL enforces access rules. Let's say if a test accidentally writes to a read-only register like LSR or reads from a write-only register like FCR, the RAL framework can flag this as an error. For example, let's say if we are trying to access a register which is only a read-only register, then our RAL model will not allow the test to write into this particular register itself. We will have that particular accessing rules using our register abstraction level modeling. And also, if this register is present inside this IP, then this RAL model basically replicates inside my test bench. This RAL model will be present inside my test bench, and this will basically replicate whatever the registers you are having inside your IP. Okay, so basically we can have a track of what are the things which are going to happen inside my IP using this RAL model inside my test bench. So this is how your RAL model is going to look like, where this is my design, and in this design I'm going to have different hardware registers. Okay, and this is my test bench. This is my test bench, and this test bench is going to have something known as register model, and it is going to have register databases, and whatever the IPs which we are going to have inside my design, same registers I'm going to have in the software level inside my register model. So whatever the changes which we are going to make inside this particular DUT design, that particular changes will be reflected over here. So this is how we are going to track whatever the changes which are going to have inside my IP using my register model, and how to update the registers which are present inside my IP, and how to make it, and what is this sequence adaptation layer, and what is this agent, and everything we are going to discuss further inside in our register abstraction level sessions. Yes. So that's all about this particular session. I hope you have understood the introduction about this RAL model, It might be little bit confusing in starting, but further if we proceed and if we try to understand with some examples, then I think it will be very clear, and I will try to help, and I will try my level best to help you to understand this particular register abstraction level in a clear manner. So that's all about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.